right. You're welcome. You're welcome once more. We want to go over to the next topic. The topic is method used in to determine the flow properties of non-Newtonian fluids. So, in order to achieve that, we want to welcome our next presenter. Please, with round of applause, let us welcome. Okay. Right. Thank you.
Good day, everyone. My name is Topsin Blessing once again, and my next topic is the method used to determine the flow properties of non-Newtonian fluids. Introduction. Non-Newtonian fluids are substances that do not follow Newtonian laws of viscosity, which states that the shear rate in a fluid is directly proportional in the shear rate, resulting in a constant viscosity. Instead, non-Newtonian fluids exhibit viscosity that varies the rate of shear or the duration of applied stress. Examples include ketchup, which flows more easily under increased shear, and cornstarch suspension, which thicken under stress. These fluids can be categorized into time-dependent, e.g. pseudoplastics, dilatant, time-dependent, e.g. thixotropic, rheopectic, and viscoelastic fluid, each displaying unique flow characteristics. The importance of studying flow properties. The flow properties of non-Newtonian fluids, such as viscosity, yield stress, and viscoelasticity, are critical for optimizing processes in various industries. In food production, for instance, the flow behavior of sauce affecting processing efficacy and product quantity. In biomedical application, the non-Newtonian nature of blood influences the design of medical devices like stents and artificial heart. Additionally, in industries like cosmetics and paint, controlling flow properties, ensuring desirable product texture and application behavior. Chemistry and engineering, providing insight into complex fluid dynamics that can lead to technological breakthrough. Classification of non-Newtonian fluid. Non-Newtonian fluids are categorized based on their flow behavior, which depend on factors such as shear rate, time, and shear history. The primary classification are time-independent fluid and time-dependent fluid, and viscoelastic fluid. 1. Time-independent fluid. The time-independent non-Newtonian fluids exhibit flow properties that depend solely on the applied shear rate and not to the duration of shear. These fluids are further divided into several types. We have bin-gamma plastic fluid, pseudoplastic fluid, and dilatant fluid. Bin-gamma plastic fluid. These fluids requires a minimum yield stress to initiate flow. Once the flow yield is exceeded, the flow with a constant viscosity. Example include toothpaste and mayonnaise. The flow behavior is described by the bin-gamma model, where shear stress is a linear function of shear rate after the yield point. Pseudoplastic fluid, also known as shear timing fluid. Pseudoplastic fluid decreasing in viscosity as shear rate increases. Common examples include polymer solution and blood. Their behavior is often modeled using the power law model with a flow behavior index less than 1. The dilatant fluid. These are shear thickening fluid where viscosity increases with increasing shear rate. Cornstarch suspension are a classic example, becoming more resistant to the flow under rapid steering. Dilettante behavior is less common but critical in certain industry applications like protective coating. Time-independent fluid. The time-independent fluid The time-independent non-Newtonian fluid exhibits flow properties that changes the duration of applied shear. These are subdivided into thiotropic fluid and rheopectic fluid. Thiotropic fluid shows a decrease in viscosity over time under constant shear, but they recover their original viscosity when the shear is removed. Paint and ketchup are typically examples. Becoming the less viscous with steering but thickening when at rest. The behavior is attributed to the reversible breakdown of the fluid internal structure. Rheopectic fluid. In contrast, rheopectic fluid increases viscosity over time under constant shear. This rare behavior is observed in some clay suspension where prolonged shear strengthens in internal structure. Rheopectic fluids are less common but relevant in specific geological and industrial constants. We have viscoelastic fluid. Viscoelastic fluid exhibits both viscous and elastic properties, meaning they can store and dissipate energy under the formation. These fluids show behavior and elastic recall and time-dependent stress relaxation. Examples include polymer melt and dough, which can stretch and return to the original shape to some extent. Viscoelasticity is critical in processes like extrusion and molding, where the fluid response to the formation affects product quality. Comparison with non-Newtonian fluids. Newtonian fluids Comparison with Newtonian fluids. Newtonian fluids such as water, oil and air have a constant viscosity regardless of the applied shear rate. Following Newtonian law of viscosity, their shear rate is directly proportional to the shear rate, resulting in a lane flow curve. In contrast, non-Newtonian fluids display non-linear flow behavior, making their viscosity a function of shear rate, time, or stress history. The key differences include viscosity behavior, flow response, application, measurement challenges. And viscosity behavior. Newtonian fluid have a single constant viscosity, while non-Newtonian fluid may exhibit shear thickening or yield stress behavior. For example, acidoplastic fluid viscosity decrease under high shear, unlike water constant viscosity. Flow response. Newtonian fluids flow immediately upon applying any shear stress, whereas Bingaman plastic requires a yield stress to initiate flow. Viscoelastic non-Newtonian fluid may exhibit elastic recovery, absent in non-Newtonian fluids. Application. Non-applications. Newtonian fluids are similar to model and predict in engineering application like pipeline flow, but non-Newtonian fluids are prevalent in complex systems like processing, cosmetics and biological flow, e.g. blood, requiring specialized measurements and modeling techniques. Measurement challenges. Measuring the flow properties of Newtonian fluid is straightforward using simple viscometer, but non-Newtonian fluid requires advanced rheometer to capture their complex behavior, such as yield stress or viscosity. Flow properties of non-Newtonian fluid. Non-Newtonian fluid exhibit complex flow behavior that distinguish them from non-Newtonian fluid, making their flow properties critical for understanding and predicting their performances in various applications. This section explores the key flow properties of non-Newtonian fluid, including viscosity and shear rate dependence, yield stress, viscoelasticity, and shear timing and shear thickening behavior, which are essential for the characterization and modeling. Viscosity and shear rate dependence. Viscosity. The measure of a fluid resistance or flow is a fundamental property of non-Newtonian fluid, but unlike Newtonian fluid, their viscosity is not constant and varies with the applied shear rate. This shear rate dependence is a hallmark of non-Newtonian behavior and is influenced by the microstructure such as polymers, chains, or particle suspension. We have yield stress. Yield stress is the minimum stress required to initiate flow in certain non-Newtonian fluids, particularly Bingaman plastic and eggshell bulky fluids. The property is critical in application where fluid must remain stationary until a specific force is applied. We have characteristics, we have measurements, applications. The characteristics, these are fluids with yield stress such as toothpaste, drilling muds and cement slurries. Only flow once the applied stress exceeds the yield stress, after which after after which they may exhibit Newtonian or non-Newtonian flow. This yield stress is a result of fluid internal structure such as particle network or molecular interaction, which must be disrupted to enable flow. Measurement. Measurement yield stress is typically measured using rheometer with techniques like stress ramp test or creep test, where the stress is gradually increased until flow begin. Ac- Accurate measurement is challenging due to factors like wall slip and instrument sensitivity, requiring careful requiring careful calibration. Application in industry processes. Yield stress determine whether a fluid will flow through pipelines or remain stable in storage, impacting design and operational efficiency. We have viscoelasticity refers to the combined viscous and elastic properties of certain non-Newtonian fluids, allowing them to exhibit like both liquid-like flow and solid-like elastic recovery. This dual behavior is common in polymer melts, gels, and biological fluids like mucus. Behavior. Behavior elastic viscoelastic fluid can store energy elastically during the formation and dissipate dissipate viscously, leading to phenomena like elastic recall, stress relaxation and creep. For example, Dove stress Dove Dove stress during kneading partially returns to the original shape due to the elastic properties. Measurement. Viscoelastic properties are measured using oscillatory rheometry, where the fluid is subjected in sinusoidal shear and the storage modulus elastic component and loss modulus viscous component and are determined. These measurements These measurements provide insight into the fluid response to dynamic leading. Application: viscoelasticity is critical in process like polymer extrusion, where the fluid's elastic response affects product shape, and in biomedical application, where the viscoelasticity of blood influence vascular flow dynamics. Shear tightening and shear thickening behavior. Shear tightening and shear thickening behavior are specific manifestation of viscosity shear rate dependence. Shear tightening fluid viscosity decreases as shear rate increases, often to the alignment of molecules or breakdown of particle aggregates. Common examples include ketchup, blood, polymer solution. This behavior is advantageous in application like pumping, where lower viscosity at high shear reduces energy requirement. Shear tightening is often modeled using the power law or cranial modes, which describe the viscosity non-linear dependence. Shear thickening fluid increases the viscosity with increasing shear rate, often due to the particle crowding or jamming in suspension. Cornstarch in water is a classic example, becoming more resistant to flow under a rapid stirring. This property is exploited in applications like impact-resistant materials and protective gear. Rheological data processing involves transforming raw experimental measurements such as shear stress, shear rate, and torque into meaningful flow properties like viscosity, yield stress, and moduling. This step is essential for characterizing non-Newtonian fluid and fitting them to in theoretical model. Data collection: rheometers and viscometers generate raw data such as torque and angular velocity in rational rheometer or pressure drop. Sorry. Okay. To my conclusion, non-Newtonian fluid characterized by their nonlinear relationship between shear stress and shear rate exhibit complex flow behavior such as shear tightening, shear thickening, yield stress, viscoelasticity, and time dependence property. Measuring their flow properties. Sorry. Viscosity as function of shear stress, providing insight into its flow behavior. Capillary rheometers, on the other hand, are effective for measuring flow through narrow channel, stimulating industry processes. In conclusion, determining the flow of non-Newtonian fluid relies on a combination of experimental and computational methods, each offering unique advantages. Rheometry provides precise rheological data (CFD), enables predictive modeling of complex flows, and imaging techniques of detailed flow visualization. The integration of these methods ensure a comprehensive understanding of non-Newtonian fluid dynamics, facilitating their application in real-world scenarios. Thank you.
All right. Thank you. Thank you.